Hi, my name is Jing Wei. In this video, I'm going to show you the project we've done last summer. This project is about controller design for autonomous vehicle. When we are driving on a highway, we may encounter some drivers in our neighbor's car that may drive aggressively or evasively. For safety, we usually differentiate neighbor drivers' aggressiveness and avoid the aggressive driver's vehicle that is close to us. The way of implementation can be also used on autonomous vehicles. My colleague has done working on the controller. This controller involves inverse reinforcement learning methods, and it needs many demonstrations for both aggressive drivers and evasive drivers for testing. What we've done was to write two controllers, evasive and aggressive driving behaviors in different road conditions, run the controllers in simulation, and record trajectories. The simulation environment contains a 500-meter four-lane highway that is built in Gazebo Simulator. One agent vehicle and some neighbor vehicles are randomly assigned on each lane. All neighbors' initial positions will be ahead of agent. When simulation starts, the agent will run faster, then overtake all its neighbors with different driving behavior, depends on which controller is used. Here are the example demonstrations of evasive and aggressive agent controller in a random condition. In the tutorial, I'm going to show you how to install and set up the program. Before installation, you need a computer running Ubuntu 14.04. I would recommend using Ubuntu 14.04.2 since it's the most compatible release for the ROS dependencies we are going to use. Here's the download link of Ubuntu 14.04.2. First of all, the program is based on ROS Indigo. Follow the guide to install and set up ROS environment. Right now, we have ROS with its essential dependencies, but not enough. The car model and its dynamic codes are used in an open source program called CAT Vehicle from Cyber Physical System Virtual Organization, aka CPSVO. It provides a very good vehicle model of Ford Escape, and the car's dynamics is strictly referred from reality. Now we are going to follow CAT Vehicles link and install the necessary dependencies for our simulation. Since those guides are pretty detailed, so I will not show them step by step in this video. Now the runtime environment is already set up. Open a terminal and navigate home directory. Then clone the code from my GitHub website. Now we need to compile the source code. Change directory to the program's main folder, then compile it. It will be more convenient if the ROS environment variables are automatically added to your bash sessions every time a new shell is launched. The final step is to source ROS variables. Now the simulation is ready to launch. In this part, I'm going to show you how to run the program. Firstly, run core programs by running ROS launch script called the start scene. In variable part, front vehicle's number can be customized in a range of 0 to 10, and the aggressiveness can be changed either true or false for switching different controllers. Then open another terminal, type GZ client to show the simulation animations in Gazebo. If this is the first time that Gazebo running on your computer, it may take some time to load the model from its database online. That might show the client is not responding, so leave it there until it revives. After the Gazebo is loaded, open another terminal and run this Python script to run control panel. Follow the instructions shown in console to start or stop simulation. Once the simulation is finished, use File Explorer to go to this directory. You will see some CSV format files in each folder. The CSV file records discrete trajectories for both agent and every neighbor. The sampling rate is 20 Hz. Now I'm going to show you some technical details about the project. Here's the structure of the ROS system. The start simulation calls load world command, which loads every model that consists highways. It also calls a ROS node called vehicle assignment, which can randomly assign the agent and certain numbers of the neighbors and load their dynamics and controller. The green boxes means launch files, and blue ones are ROS node script or actual program. Note that the vehicle assignment is a ROS node without connecting any other ROS topic. The script calls other ROS launch files by executing the commands in subshell. It seems like a dumb method because the argument from vehicle number in start sim launch file determines how many times the load vehicle launch file should be called. However, the script in ROS launch, as far as I know, cannot do recursive statement. Now I'm going to talk about the core of the controller, which is the potential field function. One fundamental purpose of potential functions is to avoid the obstacles. When the agent is getting closer to one neighbor, which becomes riskier, the agent should be more likely go away from the obstacles. Based on this logic, Gaussian repulsive potential fields were created for each neighbor whose position is inside of agent's visible range, and those repulsive potential functions were summed up. When agent is closer to one neighbor, the outcome of repulsive potential increases, which push agent to move next position that has lower potential. The directions of the next step is given by gradient vector of potential field functions. Considering the agent's role is to overtake neighbors in different behaviors, controller needs to set a goal that enables agent constantly approaches to the front. Therefore, we added an attractive potential functions that attract the agents going forward. The last step is to sum up all attractive and repulsive potential field functions together, and the controller is complete. The potential field controller can be analogized as a ball rolling downhill. On the way of rolling down, it intentionally detours the small hills on its way. I put all the related links in the video description. All the work described in this video is done in collaboration of my advisor, Jie Fu, and another team member, Yunze Zhu. Thanks Professor Fu for giving us such an inspiring topic and for guiding us in the right directions. Special thanks for my colleague, Sid, for discussing with us and give us many technical helps. Also, thanks the people working in Nest Lab for assisting some help on our way of working on the project. Thanks for watching. Feel free to like, comment the video, and share this project. I'm glad to continue offering technical maintenances to make it better.